Okay, my outstanding friends, I was just getting ready to do a bunch of stuff on meteorites, which I will do. I have some here. We're going to investigate them. We got meteorite showers coming. However, this pops up. Somebody sends me this. It says, see the past. This guy has bounced a bunch of light back and forth off of mirrors, and he says he can see the past. Well, and he's got 3.8 million hits in 2 weeks. 3.8 million hits. Now, I have been working on light for a long time. Well, forever. I understood that light is atomic vapor. All right, it's atomic vapor. And I finally was able to show this in extreme detail in about 2013, 2014, when the CMOS cell phones started to come out, smartphones. And you can use those to see photons. And you think I'm wrong? Listen to this. Okay, what I'm going to show you is stunning. They are now using off-the-shelf commercial cell phone cameras, CMOS sensors, for an experiment at CERN recently announced in 2025, April. Well, they've been doing this for a while, but they're starting to get a little deeper into this, and it's all about smartphones and how to use them for seeing photons. And they can see photons with them, and there is no question about that. CERN does use CMOS sensors for detecting photons. CMOS detection is a key focus for the future research and development at CERN. It's all about CMOS now at CERN and all the rest of them. Now, I told them CMOS would work, and they argued with me back and forth until they finally accepted it. Now, what if we could use the technology I'm talking about to carry electricity around like a little lunchbox? Let's look into this. Here it is right here. CERN does use CMOS sensors for detecting photons. CMOS technology is a key focus for future research and development at CERN. It goes down through all about the CMOS. Now, who told CERN about this? I did. Okay, so they are using CMOS to see photons. When did it start? It started when I told them about it. They're talking about it now, the specific use of commercial, which is what I was using, cell phone cameras, experiment at CERN, recently announced in 2025. This is brand new. I mean, this is new stuff. Let's just cut to the chase. Down here they say earlier work outside of CERN, which is me, using cell phone sensors for general cosmic ray detection via citizen science app. Well, we were actually seeing the photons. And this was who they're called the Distributed Electronic Cosmic Ray Observatory, DECO, whoever they are. It began around 2014. And they were looking up in the sky to see solar these cosmic rays, which are these very high energy particles. That's no big deal at all. We were seeing the actual photons. So it says, however, the application of such commercial sensors directly in a CERN experiment for detailed physics analysis is a very recent development. Detailed physics analysis. You can see the photons. All right, this is light. That's from a red laser. I wrote this 50 years, more than that ago. Transfer of energy is from light to atomic vapor. That light is atomic vapor. Just like water vapor condenses. Well, that condenses into matter. Water vapor condenses into water molecules. Very, very similar. This was our first results of seeing the actual photons. And we could see that one glowy one wasn't as glowy as the other. And they were forcing into particles in front of them, making them glow. And normally you have a wave and a particle. This is the particle. It's right in here in the wave. It's got a field surrounding it pushes through the field, glows like hell. All the other particles in the field glow as well. This, I studied more about physics and electronics and chemistry and the whole 9 yards, temperatures and everything, heat transfers, than anybody probably in history, because that's all I did, and I've done it my whole life, and I'm still doing it today. I have 4,000 videos on all kinds of things, but a lot on this. And I want this to be understood, and I was the one that told CERN about CMOS, and they're finally using it. This goes back well over 10 years. This is 2013. Don Lincoln put out this Fermilab article about this dark particle and a glowy particle, and the glowy part behind the black one, and this has all the mass, that has all the energy. I said, wow, it's exactly identical to what we discovered in the light experiments, identical. And all we were using was light. They were using huge particles, boom, slamming it together, all kinds of debris, and these were the two tiniest particles they could find. Well, guess what? Light is 1,000 times smaller than the particles they were using. So we could see the actual particles. So you saw what Don Lincoln put out. I sent him all the information. I sent him all this stuff. I said, we're seeing actual photons using the CMOS. And we can see it because we're looking at the actual light particles, which is what CMOS is designed to do. What they were doing is in huge things, and big bombs like this are smashing into the CMOS and broke it. So it didn't work. All we were doing is sitting way back here just waiting for the light to hit it. And when it did, we could see it. CMOS is unbelievable. And again, they're using it right now. They're making a big, huge thing about it in 2025. And I'm going to show you the person that I contacted 5, 6 years ago. And and she's making all these claims, a huge list of things they're doing on CMOS right now. Okay, my friends, this is an email I sent back in March of 2019 to Jolene Patter, who is I think she was at CERN. And I saw Clara, a nihilist, which I sent to her also this, and a TED Talk about the Higgs, and said electron neutrinos were undetectable. Well, let's see what she's doing now. This is 6 years ago. And here she is here, Jolene Patter. And all of this stuff is this new detectors at CERN. Now look at this. This is the one I found most interesting. There's a whole ton of these. This is just 2025, all of these articles she's written, or I don't know what it is. But they're looking for things, but they're still using particle-particle collisions, it appears. Now, there's one here, this one here. Now, what they are looking for, even though they are using particle-particle collisions, we're using light much better, and they know this. Now, I do understand what they may be looking for in these particle-particles, but you're only going to be able to make bigger particles. You're not going to be able to make smaller particles that are going to be stable. It's just not going to happen. I'll show you all that stuff in a minute. But what they want to do is observe W plus, W minus, and these Y production at the particle-particle collision. Boom, and they want to see these W plus, W minus, and the Y. Let me show you what those are, because we have seen those. All right, the crazy thing is, this exact center part is correct. The W bosons are the white ones. The Z bosons are the black ones. The gluons are these two together. The photons are two sets of these. The Higgs are where they come back together, the black and the white reattach and make a field. This is all correct. The rest is all nonsense. The rest is all made from these particles. And you see them in different forms in combinations, but it's because they smash huge things together. We only worked in here. We didn't have to work in any of that stuff. We just worked in here. And we can see those particles very clearly. All right, so they're looking for observation of W plus, W minus, and the photons. But they're using particle-particle collisions. I'll show you what they see, and I'll show you what we see. We see them clearly. They see them in more or less of a mess of debris. All right, remember, they're started with just gigantic things like this. And when they smash them together, they get things like this. Just crazy garbage, basically. But after years and years, literally, of looking through these, they found the two smallest ones were the red and the black, or whatever color of energy. So it could be red, it could be green, it could be blue, but there's always going to be the black is attached to it in light. All right, so here's CERN. I'm sorry, this is Fermilab. This is in the United States. And here's the two particles they found were the smallest particles, and they're exactly identical to the ones that we found. So I get a hold of CERN, Don Lincoln specifically, and it did not work out well at all. So I finally decided I would go to CERN and see if I could get in touch with them, and of course that didn't work out. So I took a course at the University of Geneva, which is basically CERN. And I told him, I said, I got all this stuff, I got everything, and I think you should look at it. And we basically had an argument back and forth. I said, no, we can see these because we're using CMOS designed to see light, not like you guys. You guys are using chunks like this. You just destroyed a CMOS. And eventually they came around and they said, you know, I guess you're right. Basically, they agreed. Not basically, they actually did absolutely agree. You see, here's the problem. They have no idea what they're looking through here, other than they call it a particle zoo, and it is. Look at this. And all they can do is look at it and see the littlest ones you can see. And they still don't understand that either. All right, this is what CERN and the rest of them dig through. And I mean, this is extremely simplified. That's a photon, basically. They see these black and green and red and blue particles, and they just don't know what to make of them. And what happens is these are huge, 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 gigantic things, and boom, and an X particle could be that big. An X particle could be that big. An X particle could be this big. Then they get the smallest little bits that they can find, and those are these. X could be any size because it's coming out of a big ball of debris. Basically, that's debris. They call it a particle zoo. Well, we didn't have to do that. We started with these particles right here. We started with photons. All right, this I sent back in March of 2019, 4:33 in the a.m. I was probably quite upset. And I sent it to Jolene Pater, the one that was looking for the Higgs bosons and so forth. And I said, I sent this also to Clara Nealist about the TED Talk, and Higgs and electron neutrinos were undetectable. I got them in pictures from experiments we did using pulse red laser. Anyway, so it seems the electron neutrinos can be seen after all and divided. I said, I have much to offer and would love to engage. That was to her, Jolene Pater, which is her that was doing this. She's, well, those are all, that's what they're looking through. We're looking through little tiny particles. This is her, Jolene Pater. CERN, LHC, Atlas, Dune, all these experiments. She's pretty serious into this. Now they're looking for energy values. That's okay. I go along with that 100% because I'm going to show you some energy values that I think we've created. All right, let's start here because this just tells the tale. The particle they saw at Fermilab and CERN and the other particle they saw. One glows and can get big and small. The other one never changes size, but always has a little glowy margin around the outside. And the only reason is because that's dark matter. You can't see that. It has to be on top of something glowy so that it obscures the glowiness. You're not getting any radiation. You're not getting anything coming back from that black. That's dark matter. And it is attached to the white, which is the energy right here. All right, now we have seen these. And these are the two particles. And that's exactly what you see, is that dark particle with the glowy edge around it, and the other one, which is the electron. They would call this the electron neutrino, and they'd call that the muon neutrino, and I'll show you that in a second. This is just basically what it looks like in its energetic value moving forward. The forward leading glowy one interacts with all the particles in front and excites them, so you see a little bit of excitation here. Now, down here is what CERN and all the rest of them consider the muon neutrino, which is the black ball, never changes size. This is the electron neutrino, and it goes into electron showers. This is exactly what we did. The black is now all by itself, and the white is into a shower mode because it had to come through a Venturi. The Venturi caused the light to accelerate. That is acceleration of light. There is a very, very little possibility of any other thing going on here. That is acceleration of the light. And when it hit the Venturi zone, the black bounced back. And I'll show you this. CERN is doing the exact same thing. I don't know why they won't talk to me, but they're doing it with particle-particle colliders and huge expensive things. We did this for very, very little. That is the actual particle, and that is the wave that it creates. It's always been wave-particle duality. Well, it is, because the wave is the magnetic field around a tiny little particle inside. That's the tiny little particle with a big magnetic field that comes through. Just like magnets, you hold a magnet and a magnet over here, you can feel them bumping together. Same thing, it has a field around it. That's nothing more than tiny little magnets. Basically, that's it. All right, I have or will show you the photons, and that's all they are is this. They can be green, blue, red, I imagine just about any color. But we've only seen them in the green, blue, and red because that's the lasers we used. Now, the W plus is up here. The W minus is down here. All it is upspin and downspin, and they always spin according to the polarity of the Earth. They're always straight up and down, whether we're moving that way, or this way, or that way, doesn't matter. They will never go like this, except we did actually do that. But we did it, well, I'll show you. All right, so don't forget, we're looking for the W plus, W minus, and the photons. And I believe I showed you, here they are right there. The W plus and the W minus, they're both W's, but it's just, it's up or down, that's all. Z is the black one. The two of them together make a gluon. Two gluons make a photon. The rest is just as they're gaining energy, losing energy, doing this, doing that. They mean nothing. This is what means everything. And when the W and the Z come back together, they form the Higgs. See, here she is here. Search for Higgs bosons. All of this stuff, and then the boson fusion, I've shown all of this. And this is all just recent. This is all within the last few months. All 2025 stuff. October 2025, October 2025, October 25, September. I've been posting this stuff day after day after day of all my theories. And not only that, she knows about me because I did, well, I'll show you. All right, I think I already showed you this, but I did send it to her. And I also sent it to Clara Nihilist, whoever she is, I can't remember now. This goes back 6 years here, this stuff right here. But I sent her all this stuff about accelerating the light, about light spinning, about, everything. So it's not like they didn't know it. It's just that they want to work with these big particles. I can sort of understand where they're thinking, but this is where we can get energy, and I think we can get it right away. Okay, so I went back and forth with Fermilab, Don Lincoln. He just would not listen to it whatsoever and actually insulted me, called me a tinfoil hat guy and an embarrassment to science. How he could miss these particles I have no idea how it's possible. In my opinion, he's either incompetent or he's just totally trying to mislead people so that they can continue to get funding. That's my opinion, and I believe that's the fact. Now, how could you possibly miss that? Where's his mind? And we used light, so we didn't have to dig through the debris. All right, now CERN is doing the exact same stuff we were doing. And they're trying to get down to electron showers, because here's the deal. They're using PP collisions, proton-proton. Large number of hadrons, all kinds of, but huge equipment. Decay of hadrons, creating a large flux, created neutrinos, antineutrinos, all flavors. And then they get down to where we started with electrons and muons. The energy of the neutrinos interacting within this phasor went from a few 100 billion electron volts to trillions of electron volts. And we did that just by using a Venturi. And we created the exact same thing they're doing right here. It came through with low energy showers, almost nothing. And they go, and that's that white going way up. The black came through, and most of it bounced back. Some of it went through, but it's just inconsequential. It's nothing compared to the energy here. These are the base tracks of electrons. These are the base tracks of muons. They hit and they just sort of die off. These hit and turn into showers, which I showed you. I mean, there is no question of what I've been showing you. Well, here's a better shot right here. This is, I think, from CERN. Is about Cherenkov radiation. And it's the muon neutrino, just high energy particles come in, the muon and the electron neutrino attached together, the black and the white. When they hit heavy water, they separate. The black just keeps going, and the white goes into a shower mode. Now, do you see what I'm seeing here? There it is right there. They came in together. You saw them attached, and I'll show you that again. And now they have separated. That's fusion, a fission. And then they fuse back together here. That's fusion. Fission and fusion, raw electron showers. This is what they've been trying to get to. Or they claim they're trying to get to, but it's so easy to do it that they won't, nobody will talk, nobody will discuss, and I think we're losing out. All right, here's the data visualization of the electron showers. And they're saying that high energy electrons are more likely to have a steady increase in base. Well, what are high energy? It means they're way up in that blue range where it's really coming through fast. And when they hit, they are very powerful, and they push up very quickly. This is just this. So it shows you how it's starting off, up to 40. And then at 40, we're going way up fast. It's just taking off like a rocket ship. Now when we get a little past there, there's just nothing but extreme amounts of increase in energy. This is increased energy. Now let me show you what the graph shows about that increased energy and about these increased particles, because you have to increase the number of particles in the shower to increase the energy. All right, this is exactly what I'm going to show you in a second from CERN. It comes in and it gets a little more powerful power, and then it comes up, and then all of a sudden, through here, and it's off to the races. Tons and tons of electron showers coming out of there, and tons of energy. If they're right, this is right from them, this is the number of, this is the shower maximum energy. The little U means energy, kinetic or potential, doesn't matter. You're using it right now or you're storing it. It comes through with almost nothing. And then when it hits the Venturi, the number of showers goes up like a rocket ship. Well, I'm sorry, the energy goes up to here, from 3,000 from almost nothing. That's a lot of increase. Okay, again, CERN, not me. This is energy. This is electrons. We saw the electrons coming in. and they start getting piled up against each other, and then all of a sudden they hit the Venturi and right up to there. That's the number of the maximum electrons in the shower, because it starts and it hits and then it just spreads out like that, which I just showed you. This is the energy, maximum energy. It comes in with almost nothing. It gets a little more, it gets a little bigger, and then all of a sudden, pew, at the Venturi, 3,000 times from down here. That's a lot of increase in energy. If that's right, and that's CERN, that's not me. All right, green, red, blue, whatever color, they're all the same. They have the black, and then they have the glowy little other part. Now, the black has to be on top of something that you would normally see to obstruct it. The black doesn't give off anything. It doesn't emit, it doesn't absorb, and it doesn't reflect. It's dark matter. That's where the dark matter is inside of the atoms, inside the nucleus. As a matter of fact, let me just show you that so you see Dipole Electron Flood Theory. This is where the dark matter is. It's inside. Nobody's ever seen it because it's inside. The only time you ever see it is when we did the experiments and shows it can come out of there. That's where the dark matter is. And we're standing on it right now. And you're made out of we're all made out of material stuff. And that's the only stuff that's material is the dark. The other stuff is just nothing. You can just move right through it. The dark, as it congeals solid into an atomic mass, is something you can stand on. And this is the Dipole Electron Flood Theory. My friend Oscar Rosales did this for me. Set this up, fabulous. Very simple, white electron, dark muon. And that's dark matter. And here they are here. You can separate these two. But everything there is made out of these two. 100% of the universe, as far as I can tell. And you glue two of them together is a gluon, which is heat. It's basically heat. And two back to back is a photon. After that, they don't get stable again until you get up to about 1,839 of these. And then that's one proton. So there's going to be some changes, a lot of changes. But, above the nucleus, it's going to stay sort of similar, but we don't understand isotopes. We don't understand half-lives and all that stuff in between all of the different particles on the periodic chart. Because, like, iron is not just one thing as iron, and it's always exactly the same. There are tons and tons and tons of different variations to iron. There are different weights. They have different polarities, they're all kinds of things. And every one of them is that way, every 100%. And that's what allows for the nucleosynthesis, which they don't understand that either. Enzymes transition other molecules into new stuff. Working with these enzymes, they can do millions of years of chemistry in a second. And that's how, and those are from bacteria that's in creatures. That's how we absorb things. We use nucleosynthesis. All right, it's nucleophilic invasion of stuff into our system so we can eat and grow. That's invasion. It's just not, well, give me a little carrot here and a little this and all that. No, you got to destroy it and then bring it back to what it works for you. There's a lot more to things than they understand in the subatomic range. So I just showed you the green. The red is the same thing. And all the neutrinos that, as the different flavors they call them, as they're turning into photons, they're always in this plane. It's either up this way or this way. And these will always be straight up and down to the polarity of the Earth, unless you do what we did, was force them to push each other around in circles. But all the photons are the same. This you will never see again unless somebody else does it. Green and red through the same slit at the same time. and the green forces the red to spin in circles. That will never happen. They will always just spin this way. The only time they spin this way is this field push that field this way. And what we see now is those little circular spins. You see that? That's just not supposed to happen. Those things are spinning wildly because they're being pushed by the green, which is much more energetic. Much more energetic. Now, even though that green is going this direction, it's still spinning according to the polarity of the Earth. They call it up and down spin. Depends on where the white is, up or down spin. W plus or W minus. All right, don't forget, when they're here, they're attached together to black and white. Here they separate, and here they come back together. And they come back together in what they call Higgs fields. And these are those Higgs fields. And that's that white coming in, and then now it's attaching to the black particles and spinning in circles. Now this is a very unusual shot, where these two fields are pinching this field in the middle, turning it blue, when it was normally red. That's kind of unusual, but it's turning right away back to red, it looks to me. But it jumps out ahead of everybody. It's like squirting it out of a toothpaste or something. Very cool. This was what we did all this work with, was the cell phone from 2012. So when we saw the things that CERN was doing, I said, you're doing the same thing we did. We found it using a cell phone. Of course, they went crazy. You know, I understand that. But to dismiss seeing the actual evidence, and then being really insulting on top of it, Don Lincoln, in my opinion, was insulting, and he didn't do his job. He's a fiduciary failure, in my opinion, to the human race. Because if this works, and I think it will, we should be able to at least possibly get almost free energy. Coming in here, there's almost no energy at all. Coming out of here, that's into the billions and possibly trillions of electron volts. We've separated the white from the black. That's what you do when you create energy, when you create electricity. This has no weight whatsoever. The white has no weight. It has no weight. You charge a car up and it weighs 4,000 pounds, fully charged, you drive it all day long and it's empty, it weighs 4,000 pounds, no difference. You charge it way back up again, 4,000 pounds. This white is the energy, and it has zero mass. The black has all the mass. I cannot explain how this has so much energy, the white, and has so little mass. When I talked about having no mass at all, you take a 1,000 pounds of battery, 1,000-pound battery in a car, 1,000 pounds, and you fill that car up with electricity from dead empty, all the way to full, and it gains, they claim, 45 thousandths of a gram. That's undetectable. That's like a couple grains of salt. And that's to completely fill that car back up with electricity, drive, I don't know, 400 or 500 miles, whatever it is. In a car, that would be about 60 or more pounds of gasoline. Every pound weighs about, every gallon weighs about 6 pounds fuel. Water is heavier, but fuel weighs about 6 pounds. And you fill that car up with 10 gallons, that's 60 pounds. And then you got to do it again and again and again. This stuff here, electricity, you fill it up with that white right there, no change. All right, see that? That was my patch when I was in the Army up in Alaska working on the nuclear missile sites. What happens in a nuclear bomb is everything goes out with the energy first, and then the black heavy particles follow it, and those are the things that knock things over. The white particles come out first, just burn things up, and yes, I can prove that. Okay, this is World War II. They're trying to figure out what a nuclear bomb does, how it reacts. They got a a real heavy-duty, facing that way enclosure, top quality cameras. They got everything wired and checked out, and they got all, it's a little, sort of like what you'd expect in a little town. So here's what's going to happen. I got to run extremely low speed. And what we will see first is the flash. Boom. Now everything is just smoking. It's just smoking. No, there's nothing moving. There's nothing moving at all. The wires are smoking. The poles are smoking. The roof is smoking. Everything's smoking. But nothing has moved. That's an atomic bomb. That's the energy part. Now comes the mass. Boom. And that's the two separate events of an atomic bomb. And that basically shows what I'm saying is true with the dipole electron flood theory. There is two complete separate pieces to matter. There's the dark and then there's the white energy. And not too hard to understand once you understand it. And then for some reason, and I really can't pin that down, they become more or less stable at certain quantities of these little particles. And I mean, when I say more or less stable, there's a ton of isotopes. What an isotope is, it means that if you say this is stable at 10,000 particles, well, you might have that many. That's not 10,000, it's like 9,500. It's still stable. Well, it's an isotope of that atom. And perfect stability is right exactly with the right number of these particles. Very rare. It's extreme stability, I think, is rare. Mostly they're in isotopes which are pretty close to stable, but not stable. And then there's a lot of stability. I would like to know what the ratio of stable to unstable elements is. That would be interesting. All right, this is not something people consider very much. The relative abundance of isotopes for a given element is typically constant in nature. It means that each one of these has so many of these different little particles that they see in the same ratios, approximately. On both sides, they may have too many particles and they may have not enough particles. That's what isotopes are. And then they break down to form other atomic nucleuses. It's called nucleosynthesis. And they can decay upwards and they can decay downwards. It depends on literally what enzyme is working on that molecular structure, that atomic structure. All right, we have established in CERN that if you can create these electron showers and separate them, you can increase the energy exponentially. And we have done just that. Whenever you see luminosity, it means an increase in energy, and this is about as luminous as anything is ever going to get. Now, what does that do? Well, it could do this. We could send lasers through a venturi and put a harvester right on the other side before the white gets back to the black, and just send the white down. You could carry it around in a little lunchbox. The white weighs nothing. Light is light. The white weighs nothing. So if you could get this to send it down through a photodiode, it goes through it as a gate, you can't go back. It's down inside. Either you use it or you store it or you do whatever you want with it. You don't need any huge contraptions or any of that stuff. I would think this should have been looked at 10 years ago. And I told Don Lincoln at Fermilab that he will face his day with this, because he was tasked with interfacing with other scientists in the rest of the world, and that he absolutely did not do that. And nobody in their right mind could see this and not understand these are the same particles as these. And we started with light, which is the smallest. They started with huge things, but these are the smallest they found after like 10 years of digging through debris. All right, and here was his article in 2013. And not long after that, I approached them. I approached Fermilab, all of them. I was the one that said you can use CMOS. They would have never done this. They're just starting to get into it now. Well, they've been doing it for a few years now, but now they're looking to get into photons instead of big heavy particle colliders. They're not getting anywhere with the big heavy particle colliders. They're dangerous. They're destructive to the environment. All kinds of problems with that. This is where they should be at, and we should be investigating getting some free energy. If you could walk around with something like this and click it anywhere you want, AC, DC, 50 cycles, 60 cycles, anything you want, right out of that little box, carry it around with you, strap it to your back, whatever you want. Safe, efficient, off-the-shelf components, ready to go. So, all right, I'm going to leave it at that, but I think it's time that some of the things that I have been doing will be allowed to be seen. I know that I have changed things for the high and mighty, but life goes on. You cannot escape from this. There is no escape anymore. It's just denial, and it's starting to look extremely bad for the people we trusted to teach us truth and reality. I have found nothing but a stone wall, and I mean a stone wall. And by the way, light comes through, makes a field surrounding the particle, and it spins. It doesn't flap like this. It spins like that. Again, yes, I can prove that, because here it is right here. Spinning like this. Sometimes it goes that way, sometimes it goes this way. But once it gets through the Venturi, they stay away from each other. They create these stripes. And those are the interference patterns. And you can see the head of a drill here, drilling right through there. That's what light does. It spins. I think I have enough evidence to support everything that I've said. And if I don't, please contact me. And if anybody at CERN or Fermilab or any of the agencies says that I'm telling you stuff that isn't true, I want them to come forward and let's discuss it. That's all. I don't want to be nasty. I just want to discuss it. And I think I've sent it to everybody. I've been sending it over and over and over, and they don't want to hear about it when you have the kind of evidence I have, because they can't support their side of it. And once you can't support your side, it seems to be that the truth doesn't matter anymore. If it's not in support of your side, well, I don't want to talk about it. That's what I've heard. That's all I've heard in the last 15 years. It's time to work reality into the equation. All right, I love you all. Bye.